Hello and good afternoon to everybody who's got their GCSE exams coming up this week. So I'm Lewis from Physics Online. I've got a couple of websites. I guess what you might be interested in if you're watching this live stream is GCSE Physics Online. I've got videos that cover everything. So if there's something that you're not quite sure about that's coming up for paper 1 this week or paper 2 next week, head over to GCSE Physics Online and you can find everything that you need there. I can see that people in the chat are putting in emojis. NFF747, basically I think you found the emoji button. Good afternoon. Hello to everybody else who's watching. And of course hello to any A-level people who've just done their real A-level physics paper 2 exam this morning. So if you are an A-level person, hello, hope it all went well, and if you want to stay around in the chat and answer any GCSE questions, then feel free to do that. So hello to Henry, to Amber, to Victoria, everybody there who's saying hello. So basically what I'm going to do now is go through complete revision for AQA GCSE Physics Paper 1. The reason being that most people doing AQA most people doing GCSE are doing AQA, and therefore I'm going to concentrate on that because it's going to help the most number of people. And what I have is a completely free revision guide. I've put a link to it pinned to the top of the chat in the live, and also for those watching afterwards, in the description beneath this video I've got a link so you can basically download this. So this is what I'm going to be working through today. And as I'm sure you should be aware now, basically energy, electricity, particle modelling gases and atomic structure. This is all stuff that's covered in paper 1, and that's if you're doing both trilogy, the combined science, or if you're doing the separate, the triple physics. So basically that's all happening in paper 1, and then paper 2 gets a little bit more tricky in some ways, where we've got things like forces, waves, magnetism and electromagnetism. I think the electromagnetism is probably the hardest bit of GCSE physics, and then we've got some lovely space physics for those of you doing the triple science. So yeah, basically today we're just going to be going through these things, and I'm going to start by revising and summarising energy. So basically what I'll be doing during the stream is going through in order in the way that things come up in the specification. So if you do have questions about like nuclear physics, nuclear fission, nuclear fusion, whatever that might be, that will be coming up later in the session. But I'm basically going to go through from looking at energy to looking at the other kind of sections after that. Right, so yeah, should we go? Right, am I covering combined science higher? Yeah, so basically what I'm going to cover here will be suitable for anybody doing foundation level and also students doing higher. And of course, what I'll try and do as I go through this, I'll just let you know if the stuff I'm talking about is for higher only, and also if there's stuff which is for physics only. So those of you doing the triple science, I'll do that in another colour, this kind of light blue colour. So if you're doing trilogy, the stuff I write in light blue you don't need. Okay? Yeah, oh yeah, by the way, I did call this grade 9, but to be honest, the stuff I'm talking about here, so I'm just going to stop some people. Basically, the stuff I'm talking about here, although I said it's grade 9, this will definitely help you get towards that grade 9. And it might be that you want to get a grade 6, so maybe going from a grade 5 to a grade 6, the stuff I'm talking about is still going to help you. And even if you've done no revision, even if you haven't looked in your revision guide or kind of really paid attention in school, even if you're just wanting to scrape through GCSEs, then the stuff I'm going to talk about now can really help you just get those extra couple of marks in the exam. How long is a live going to be? I don't know. It might well be 2 hours long, maybe 3 hours. I don't want to be here longer than needed, but basically we'll just see what's going on. So if you know nothing, is it worth watching it? Of course it is. If you know nothing, then you really do need to watch this. Okay, so basically this stuff here, you should be familiar with a lot of the content. And what I'm going to be doing is just going through it step by step. It might be a little bit small to see, but basically we'll just go through stuff from the beginning. So we need to think about, first of all, the way that energy is stored. So energy is very much like our way of accounting for things, and it's a quantity, so it has a unit and it's got a number. So you might have 10 joules, 20 joules, 30, whatever it might be. We can quantify the amount of energy that an object has stored. And basically it says here some kind of common examples. So maybe something projected upwards, a moving obstacle hitting an object accelerated by a constant force, a vehicle slowing down, a kettle heating up water. And really when it comes to energy, you need to know about kinetic energy. So kinetic energy is the energy stored by a moving object. So this is something which is moving. We also have gravitational potential energy. And this is going to be the energy that an object has due to its position in a gravitational field. So basically you take something, you move it higher in a gravitational field, we increase its store of gravitational potential energy. Another one that comes up quite a lot is elastic potential energy. And this is really due to an object that might be stretched, it might be squashed, or it might even be kind of twisted. So basically what we're doing, we're applying a couple of forces to something, and a common example of that might be a spring. So elastic potential is another one. We also have thermal energy, sometimes called internal. And basically this is the energy that something has due to being, or that really depends on how hot it is. So the hotter an object, the more energy it's going to store in that thermal store. And then we've got another one, probably a bit more like chemistry, I guess, but sorry, not chemistry. We've got chemical energy. And this one here is kind of the odd one out, because if we think about the energy stored in the chemical store, it's a lot harder to calculate. So we've got chemical energy as well. And then we've got some other ones. You might have energy due to the magnets, maybe energy due to the electric field, or energy due to the nuclear, kind of the way that I guess atoms or nucleons, the protons and neutrons are arranged inside the nucleus. So I guess we also have nuclear, we have magnetic, and then we've got this kind of electrical potential as well. So these ones here don't come up that often. These ones here are the main things we need to know about. Okay, so right. Yeah, so what I'll do is keep an eye on the chat. If people kind of post stuff that's not appropriate, I'll just ban you forever. I think it's the easiest way of doing it. So basically that's your warning, but I'm sure it should be absolutely fine. If you're A-level, if you're GCSE, help each other out in the chat, because a lot of you might have questions that other people can answer. Now, of course, with all of these things here, what we have are energy stores. Okay, so these are ways in which energy can be stored. And what we have to think about is how we go from one store to another. And the way that I've kind of often thought about it and kind of explained it in my videos is you basically, I've just drawn the energy store in a box, and maybe you've got the starting store, and then you've got the store at the end, and then we've got an arrow to show the transfer. As what we do is we can transfer energy from one store to another. And the way that we can transfer energy, I'll just write these down in a different colour. We could have heating. So maybe you're heating an object up, and that means we're going to increase its thermal store of energy. There's going to be by doing electrical work. So this is maybe when you're moving charges around a circuit, and that's going to allow energy to be transferred from maybe the chemical store inside the battery, and then it's going to be radiated out into other kind of stores in the room, for example. We also have radiation, which basically means that not so much it's ionizing radiation, it's not nuclear radiation, this just means we've got waves. So it could be radiated out by a sound wave, or it could be radiated out by light, or indeed any other part of the electromagnetic spectrum. So this could be things like infrared as well. And then the final one that we have is we've got mechanical. A mechanical is the most common form of energy transfer, because mechanical work is basically when you've got a force acting over a distance. And when you multiply a force by a distance, this tells us about the quantity of energy that's been transferred, the amount of work done. Okay, right. Cool. Okay, so basically, so I'm just reading the comments. I've got somebody saying that the AQA A-level physics paper 2 is very nice. Kyle, brilliant to hear you saying that. They did correct their ways this year from the previous years. Cool, that's awesome. Okay, right, so we've got all of these things here. Now, these are stores, and these things over here are transfers. And often there might be maybe a 1 or 2 mark question just asking about how the energy was stored at the beginning and at the end. Now, the key thing about these stores is we can actually put a number to this. And of course, we can then use the unit of the joule to work out the exact amount of energy that something has. Now, a lot of this is basically given to you in your data sheet. Now, the data sheet that you're going to be given is something that you need to rely on. So every time you do a calculation, double check with your data sheet just to check that it is actually the right equation that you're writing down. Now, in the data sheet itself, they will give you the word equation, but there's also going to be a symbol equation to the side. So what I'll do is just write down some of the equations. First of all, we can work out the kinetic energy of something, and this is equal to a half mv squared. So we've got the mass of the object multiplied by the speed squared, and you only square the speed. So for example, if you had an object that had a mass of 2 kilograms and it had a velocity of 3 meters per second, then the kinetic energy would be equal to a half times 2 times 3 squared. So when you put it into your calculator, and that's another tip I'm going to say, is that don't try and do stuff in your head. You can do that in your head, but it's always worth checking. So we've got 3 squared, which is 9. We're going to multiply that by 2 and multiply that by a half, which is equal to 9. So that would be equal to 9 joules. So even if you have a very simple calculation here, always double check on your calculator so you don't lose little marks here and there across your paper. Okay. That will be on the equation sheet. You don't need to remember it. The next one is gravitational potential energy, and this is the energy that an object has due to its position in a gravitational field, and this is equal to, this gravitational potential energy is equal to mgh. Basically, the mass of the object times the gravitational field strength times the height through which it's moved. And this really tells you about how much energy something has gained as it's got higher, or how much energy it's lost as it's got lower. So that's gravitational potential energy. Very similar to that, we've got elastic potential, and this is what we do when we stretch an object. And the way that AQA have this is this elastic potential energy is equal to a half ke squared, where E is going to be the extension of that object. It's not the total length of a spring, but it's how much longer that spring has got, or even how much shorter a spring has been compressed. So we can look at elastic potential, maybe if you stretch a spring, or if you were to compress that spring. Okay, you don't have to remember that, Soraya. So basically, a lot of this stuff here is stuff that is given to you. So all you need to do is know where to find it in your equation sheet. The next one is thermal energy, and the way that we can look at the thermal energy is we can basically say that delta E is equal to mc delta theta. And this will tell us about the change in thermal energy when something is heated up. And the letter that we use for temperature is the Greek letter T, which is theta. Or it's a bit like the Greek letter T. So theta is going to be our change in temperature. And here C is what we call the specific heat capacity. Okay, and basically if we think about what C means, well, we could take this equation and we could actually rearrange it, and we could say that the specific heat capacity is the energy required to heat up 1 kilogram by 1 degree Celsius. Okay, so it's the energy needed to heat up 1 kilogram of a substance by 1 degree Celsius. An example of that would be water, which is a very common thing that's mentioned. And if we think about the specific heat capacity of water, that's actually equal to 4,200 joules per kilogram per degree Celsius. And this basically means that if you had 1 kilogram of water and you wanted it to get 1 kilogram, sorry, if you had a kilogram of water, you wanted it to be 1 degree hotter, you'd have to supply 4,200 joules of energy. So imagine you had a kettle that had 0.5 kilograms of water and you wanted to raise the temperature by 30 degrees. We could actually look at the energy transferred, because this would be equal to m times c times delta theta. So it would be the mass of water times the specific heat capacity of water times by the change in temperature. And that would then be equal to, I'm just making these numbers up, that would be equal to 63,000. And because this is the energy change, the units that we'd use would be J. Okay, yeah, so somebody here, Kyle, just says basically they still have the data sheet. Yeah, the good thing now is that just like in A-level physics, you're not being assessed on your ability just to remember equations. You're going to be assessed on your ability to actually select the correct equation, find the right numbers and put it into your answer. And you do get the equation sheet. Somebody wants me to say a certain number. I will, but only, let's have a look at how many people have liked the video. I will say that number. At the moment, I'm on 11 likes. So I might say the number when we get to that number of likes. So what I need everybody to do, if they haven't already done so, is like the video. And when we get to that number, okay, we're on 12 likes at the moment. Let's have a look. So basically, this is me watching myself. That's weird, isn't it? What's the time delay between doing something and then they're seeing it on YouTube? Okay, so, right. Yeah, basically 21 likes. Thank you, everybody. That's amazing. 27. By the way, has everybody subscribed? If you subscribe to me on YouTube, that means you can also post stuff in the chat as well. Right, I'm going to keep an eye on the likes. At the moment, we're still on 27. So basically, that's energy stores, that's energy transfers, and they're the equations that you are going to be given in the exam. Right, so what I'm doing is, for those who've just joined, I'm basically working through what the specification says part by part. Okay, the next thing we need to know about is power. So energy is something that is measured in joules, and power is related to this. The electrical power, or indeed the mechanical power of something, is just equal to the energy transferred per unit time. So if you want to work out the power of something, we can work out the energy in joules, and then we divide that by the time in seconds to get the power in watts. And the key thing to remember here is that in science and in physics, we always use standard units for everything. So that means if you're given a question where you might have kilowatts or you might have milliseconds, always convert all of your units into what we call our standard SI units. So this would be, if you've got a mass, convert it into kilograms. If you've got a force, convert it into newtons. If you've got a speed, convert it into meters per second. Any distances need to be given in meters. What else do we have? Any energy is going to be in joules. Any time is in seconds. So these are the kind of common things that you need to use. There are so many examples I've seen, particularly for the time, where they might give you the time in minutes or hours, and you've always got to convert everything into these standard units before you put them into your equations. Okay, right, we're now on 44 likes, which is good, and thanks to all those 44 people. But yeah, am I going to do 3 hours straight, or am I going to have any breaks? I reckon I might need to get a break to get a cup of tea or a drink, but at the moment I'm sort of just planning on doing it straight. Okay, and of course you can re-watch the live stream whenever you want to. Okay, so we can calculate the power by looking at the energy transferred divided by the time in seconds, but there's another equation that is basically the same thing, and it says power is equal to the work done divided by the time. And basically work done and energy are pretty much the same thing. You do work on an object and we transfer energy to it, or energy is transferred to an object and work is done. So think of work done and energy just as two words that basically mean the same thing. Okay, Right, let's keep going. Give examples that illustrate the definition of power. For example, comparing the height that two electric motors that lift a weight through the same height but in a different time. So basically, let's imagine we've got a very simple scenario where we've got a table, and on the top of that we've got a little electric motor, and this thing here can basically spin round. And what we have is on the end of this we've got like a spindle, we've got a piece of string coming down, and that goes to a mass. And as the motor is spinning around, this thing here is going to move up through a certain height. Could we work out the power of that motor? Well, the power would be equal to the energy transferred divided by the time. And if we wanted to look at maybe an object which is going through a certain height, this might change its height, h, through a certain amount of time, and we might know the mass of that object in kilograms. So this would allow us to work out the power. So for example, let's imagine we had the mass equal to 2 kilograms. The gravitational field strength is 9.8 newtons per kilogram, and the height that it goes through is equal to 0.60 of a metre, and the time it takes to do this is 12 seconds. What I've done here is I've basically written down everything that the question might give us. I've just made the numbers up, by the way, so I don't know what the answer is. Could we calculate the power? Well, the first thing we can do is we can look at the energy that that object has gained. Okay? Sorry. And basically the energy is equal to m times g times h, because what we have here is something gaining gravitational potential energy. So the energy gained is going to be equal to the mass of 2 kilograms times 9.8 newtons per kilogram times 0.60, and just to work that out, this is equal to 11.76 joules. Okay, so that's the energy gained. What's the power of this electric motor? Well, the power is equal to the energy transferred per unit time, and that's going to be 11.76 divided by the time, which was 12 seconds. So if we take the previous answer that I'm going to leave to all the significant figures on my calculator, divide that by 12, this is equal to 0.98. And of course, if it's the power of something, the energy transferred per unit time, it will have the unit of the watt, capital W. Anyone here actually listening? Okay, right. Let's see. How many likes have we got? We've got 46 likes, just 21 away from the magic number. The other thing I would say is it's really important that when it comes to any symbols that you're using or any units, you have to be exact. If you give the answer for joules as a little j, that's incorrect. If we're going to give an answer for a joule, it has to be a capital J, and that's going to get you the mark. If you put a lowercase w, that's incorrect, but a capital W to represent watts is correct. Okay, kilogram is a little k and a little g. A metre, the mass of something is a little m. And these things here are important. If you've got the force on an object, that's always going to be a capital F. You don't have a little f because that thing's just incorrect. And there are so many examples I've seen where students maybe write down an equation like this, F equals ma. That is not correct because they've used the wrong F to represent the force. Because what we do instead in physics is we use the same letter for different things. So capital F is a force, lower f is going to represent the frequency. So this thing here can't be correct. Does that make sense? So a lowercase w could be, I don't know actually. J is often sometimes used as a vector. You might have an I and a j vector. A small w, I'm not quite sure what that represents. Good question though. Okay. Right, there we go. So that stuff there is all good. The next thing you need to know about is that energy is always going to be conserved. And basically, if you've got a closed system, whatever energy you start with is the energy you have at the end. And the other thing is that energy cannot be created or destroyed. Instead, what happens is we just transfer the energy to a different store. Okay, so if an object maybe initially has kinetic energy and then it comes to rest, what's happened to all of that kinetic energy it initially had? Well, it's probably going to be dissipated to the surroundings through heating. So that it's going to increase the thermal store of the surroundings as the kinetic energy decreases. Okay, do you get marks for writing the formula? Yes, you do. Even though the formula is given to you in the data booklet, you're going to get a mark for selecting the correct formula. So even if you're not quite sure about the final answer, even if you were to just look in the data book, find the appropriate formula and write that down, there's a good chance that you could get a mark for selecting the appropriate formula. And of course, once you've done that, it's easier then to kind of start putting in numbers to then start your working out. Okay, right, the next bit is a bit about energy. This bit here kind of gets a bit more wordy. It talks about ways of reducing unwanted energy transfers. One of these is if you've got lubrication. This means that you're going to reduce friction between moving parts. So this is why it's really important to make sure that the engine oil is topped up to the right level. So if you've got something which is well lubricated, there's going to be the least amount of friction. We're going to increase the efficiency. You might also have insulation, and this is going to make something like a house, for example, much more energy efficient because we reduce unwanted energy transfers. So this could be cavity wall insulation, this could be double glazed windows, it could be loft insulation. What these do is they slow down the rate of energy transfer out of that house. And also, the other thing that we might have is you might make something more streamlined. So if you've got something like a train, for example, you want that train, especially if it's going really fast, to be pointy, so you have less air resistance, and again, that's going to reduce any unwanted energy transfers. Okay, the next thing then is about efficiency. So the efficiency of an object, there are two different ways in which we can calculate it. It's either looking at the energy or it's looking at power. So what we think about is the useful energy out over the total energy in, or we can also look at the useful power out over the total power into something. And it's basically the ratio of these two things. So for example, if you had something where we put in 100 joules of energy, and then what we actually get out is maybe 80 joules of useful work being done, that means there's going to be 20 joules which is wasted. So imagine we put in 100 joules, we get 80 joules out, and then we lose 20 joules. Now, of course, the total energy can't be created or destroyed. It's just going to be transferred to other stores. And if we wanted to look at the efficiency, it would be equal to 80, the useful energy out, divided by the total energy in, which is equal to 0.80. And when it comes to efficiencies, we can either give a number from 0 to 1, or we can give a number from 0 to 100%. Because basically an efficiency of 0.8 is the same as an efficiency of 80%. Right, we're on 65 people at the moment. We'll see, because you're children and I'm a massive child as well, if we get to the magic number. Okay, so we're on 66. One more to go. Is everybody excited? Is this the most exciting part of your revision today? We've got, oh, it's gone down to 64. Somebody's unliked it. Are we going to get people unliking the video so we never get to that number? Okay, right, we're still on 64. I'll keep an eye on that, and if it gets higher, I'll let you know. Okay, the next thing is we need to think about energy resources. So the other thing we need to think about is actually how does the world actually keep going on? And that means how do we have enough energy for me to be sat here with the warm kind of air coming through, or the air conditioning on, or the studio lights, or my camera working? How do we get that energy from somewhere deep underground or outer space into the homes, the schools, the offices and the houses. And this is where you need to think about energy kind of resources. There are two main types. We've got renewable and we've got non-renewable. And what you need to know for every one of these are the pros and cons. Okay, oh, we got to 76. That's kind of the opposite, but yeah, okay, there we go, I'll do the hands, whatever. Yeah, right, yeah, so we did get to 6, 7. Okay, right, we've done it, let's move beyond it. Okay, right, so let's see what people are saying. Yeah, so basically renewable, let's do non-renewable first of all. There are two main sorts. We've got oil, we've got gas, and we've got coal. Okay, so these ones here are fossil fuels because they're basically made out of dead dinosaurs and other things like that. In actual fact, if you've got a toy plastic dinosaur, it's made out of real dinosaurs. It's just the real dinosaurs died a long time ago. So plastic dinosaurs made out of real dinosaurs. The other type of non-renewable thing, the energy resource that we might have, is things like uranium. Now, uranium is an element that is mined underground and then it's put into nuclear fuel rods and it's used in a nuclear fission reactor. And so we tend to use uranium or sometimes plutonium, but it is non-renewable because once it's been used up, it's gone forever. So these ones here are fossil fuels. We also have uranium. The other thing though is that we've got renewable things which we can use to generate electricity. So what have we got? We've got people saying stuff here in the chat. So let's see. Yeah, so what are the renewable types of energy? We've got solar, we've got wind, we've got biofuel. What else do we need? Hydroelectric. There's basically a massive list. We've got solar, wind, hydroelectricity. We've got geothermal. We've got wave power. We've got tidal. There's probably some there that I've forgotten. Okay, now, the key thing here is that in order to generate electricity, what does streamlined mean? So streamlined means that things are maybe smoother and they're more pointed. So if you think about the difference between like a Land Rover, which is kind of not particularly streamlined, and you compare that to a racing car, which is much lower to the ground, a lower cross-sectional area, it's much smoother. The more streamlined something is, the greater the air is going to move around it. And that means something is going to be more efficient. Okay, so here we go, renewable, non-renewable. Now, a lot of these have the same things in common, and this is because in order to generate electricity, what we need to have is we need to have a generator. And for those of you who've already been studying stuff for paper 2, you know how if you've got a coil moving in a magnetic field, we can use that to generate electricity. Now, what turns the generator? Well, we need to have a turbine. So the turbine is basically spinning blades, and the thing that causes the turbine to move is often something like steam. So where do we get steam from? Well, we basically need to have something that gets very hot. And so what we do is in a nuclear fission reactor, we have uranium that as it splits apart, it gives out heat, or there's kinetic energy of the products, which then goes to the thermal store of that water. Coal is burnt to make hot things, coal is burnt, and oil is burnt. We also have biofuel that's burnt, and that then makes steam, which turns a turbine. We also have geothermal, which is hot, and that makes steam to turn the turbine. But I suppose the other thing that we can do, as I'll put this in green, is we can just use water, which is moving really quickly to turn the turbine. So how do we get the water moving? Well, we basically have tidal, we've got wave, we've got hydroelectric. All of these have water that turns a turbine. And then we've got wind, which basically turns the turbine that makes the generator move, and that gives us electricity. So, right, what are people saying? Okay, no chat, please. Right. So, is it buffering or is it okay at the moment? It seems to be okay for what I can see over here. Okay, so all of these things basically have something spinning. So you've got the wind makes the big turbine blade spin, which causes a generator to move, and that then means we generate electricity. There's one of these though, which is the one which is the odd one out, and that's going to be solar. So with solar panels, what we do is we directly take the energy from the sun that is then used in photovoltaic cells. So with solar panels, what we have is a photovoltaic cell, and sometimes they're known as a PV cell. The word photo means light. The word voltaic is to do with electricity, so we basically get light, electricity, and a solar panel doesn't have any moving parts. It's just got these small cells which directly generate electricity when they're illuminated by the sun. And for all of these, right, basically what I'm going to do is just get rid of some people. Yeah. So basically, this one here is the one that doesn't have any moving parts. Now, all of these are pros and cons. It's really quick to have a gas-powered power station or a gas-fired power station to turn on and off. So we can basically turn on the power station, get more electricity when we need it. Uranium, basically in a fission power station, there's going to be no CO2 emissions because we're not burning anything. So that's a really good thing. But on the other hand, the radioactive waste can last for millions of years, which is a bad thing. Wind and solar, they're renewable, they're getting cheaper. But the problem is, if it's not sunny and it's not windy, we can't generate electricity. We can only use geothermal in certain places like Iceland. We can only use hydroelectricity where there's hills. We can only use tidal and wave if you're by the sea. Yeah, there we go. So there we go. A lot of this, by the way, this is combined science. So those are basically the different kind of energy resources, and you need to know the pros and cons. Ideally, you want to know 2 positives and 2 negatives for each of these ways of generating electricity. And that is basically all you need to know about energy resources and energy for AQA GCSE physics. The next thing we're going to do is we're going to do a little bit more about electricity. So yeah, it's a bit of Lego here. You might see in my other videos where I've got Lego in them. Basically, I've got everything here for everybody, and I'm going to be going through triple as well. Now, for students who are here at the moment, it doesn't matter if you're doing combined trilogy or the separate triple physics, the energy content is the same. And when it comes to the electricity part of the course, most of that is identical as well. So the only thing extra you need to know about if you're doing triple science is static electricity. Okay, right, here we go. Let's see what the comment says. Okay, comments all good? Right, 77 likes. Can we get to 100? Let's see how we get on. Right, should we just keep going? I'm just going to have a quick sip of drink and then we'll get started looking at electricity, which I think is probably the hardest part of paper 1. I think energy is okay, particles is okay, atomic is okay. I do think that students tend to find electricity a little bit more difficult. Okay then, right, so what do you need to know? Draw and use standard circuit symbols. Okay, right, so let's have a look. Circuit symbols that you need to know about. Hopefully this is just revision. You've got a filament lamp, so that's just your standard light bulb. I'll just zoom in a bit. So that's basically a lamp. You've got this thing here, a rectangle. That is a resistor, and that's basically something that we can use to control the amount of current in different parts of the circuit. We've got this thing here, which is a cell, and if you have a series of cells joined up next to each other, what we have is a battery. So this one here is a kind of standard kind of power source. It's kind of storing that chemical energy, which can then be transferred around the circuit. The next one is right. The next one, by the way, just keep all the chat nice in here, otherwise I'll just see if people are banned. Can free body diagrams come up in paper 1? Corral, I don't think they can. Yeah, so I reckon free body diagrams are very much under the forces module, so that would come up much more in paper 2. So you've got a battery here, and of course when you've got a resistor, we have a load of other things which are like this. So one of them that we have is we have this thing here, which is a variable resistor. And this is a resistor whose resistance you can change, and you basically have a little dial or something like that. You can change the resistance of that component. We also have a component that looks like this, and this one here is a thermistor, and this is our thermal resistor, which changes its resistance with temperature. And then the other thing that we have over here is a type of resistor that changes its resistance when light is landing on it, and we call this a light dependent resistor. Okay, so just a few components there that you need to know about. We also have something that allows current to go one way in a circuit, but current going in the other way is stopped, and this thing here is called a diode. And then we've got something which is like this, which allows current in one direction, doesn't allow current in the other direction, but it also gives out light. And this thing here with the light coming out is an LED, so a light emitting diode. So there we go. Yeah, basically they're the main kind of circuit symbols that you need to know about. The only other things that you might have in a circuit are an ammeter that has to go in series, and that measures the current going through it, or we have a voltmeter that measures the potential difference across a component, and therefore it has to go in parallel with that component. So these are the circuit symbols that you need to know for the next 24 hours, and then you can forget about them for the rest of your life. Okay, unless of course you are doing A-level physics. If you're doing A-level physics, by the way, let me know in the chat if you currently do A-level physics or you're thinking about doing A-level physics for next year. Oh yeah, switch. People are saying things. Yeah, I've forgotten. A switch just looks like that. A fuse looks like a resistor, but it's basically got a wire in the middle. So this thing over here is a fuse. Okay, Ohm's law, more like Cole's law. That's random. Yeah, so basically, if you're doing A-level physics, I also have videos that I'm sure some people in the chat can say that they are useful videos and live streams and things. I've got these books as well. So this book here is my daily workout. It's book number 1 for A-level physics. So if you finish your exams, this is basically all the preparation you need starting in July. So have a couple of days off after you finish your GCSEs. And then I've got questions for you to do every day over the summer. So 5th of July, 6th, 7th, 8th, 9th. And basically, if you do this work, then at the start of your A-levels, you'll be really happy with all of the kind of the new physics you're going to be learning about. So you can buy the book on my website, or you can buy it on Amazon. And there's basically questions here that go on throughout the whole year. And in actual fact, I've now got 6 books. Well, I've got 5 books, and book 6 is coming soon. So I've got questions for every single day of your A-level physics course. Somebody used the book, says Isaac Davis. Great name there. I can recommend, if you're doing A-level, Paul, then you should definitely think about it. Yeah, and if you are doing A-level physics, there are, do I have a physics 6-pack? Not quite, I'm still working on the full 6-pack. Do you know what? That's a brilliant name, isn't it? You do the daily workout, you get your 6-pack. Oh, do you know what? Andrew, that is a genius bit of marketing there. Okay, right. Is A-level physics okay if you get an 8 in triple? Yeah, absolutely. You'll fly through A-level physics. If you've got like a grade 7, 8 and 9, you're going to fly through it. Grade 6, you're going to be fine. You just got to keep working hard at the beginning. Here we go. Kyle says, those books, the live streams and everything he does, you can be doing for the year for your revision. Okay, cool. Right. Yeah. GCSE A-level Maths 2026. Very good, thank you. Yeah, right. Okay, let's keep going. These are the circuit symbols you need to know about. Then, of course, what we'll just consider first of all is the most basic circuit where we've got a cell and we're going to have electricity going through a resistor. Now what we can do is put an ammeter anywhere in that circuit, and that's going to tell us the size of the current. Now on the cell, the longer side is the positive end and the shorter side is the negative end. And if we had a circuit like this, we say by convention, conventional current goes from positive, then it's going to go around the circuit to negative. So this thing here, I, is the intensity of current. And it goes from positive to negative if it's conventional current. And what it means is that basically this is equal to the charge transferred over a certain amount of time. So current is the rate of flow of charged particles. And we can basically take this and say that Q is equal to IT, quit. So this one here is an equation that you're given, but this is what it really means for current. So current is basically the rate of flow of charged particles. And that's what we actually mean by electrical current. Now the other thing here is that although we say conventional current, so conventional current goes from positive to negative, the actual electrons, the little particles which are negative, and you have electrons, that the particles that travel in a wire, they're going to be repelled by the negative end and they're going to be attracted to the positive end. So what we actually say is that the electrons are going to be travelling in the opposite direction to conventional current. So although conventional current goes from positive to negative, the electrons, the small particles, the free electrons which are free to move in that wire and can be used to pass on the energy, the electrons go from negative to positive. So that's the big difference between conventional current and the way the electrons actually move. Okay, so it says here that you need to know about charge equals current times time. The current has the same value at any point in a closed loop in a circuit. And then we've got probably the most important equation of all. And this basically says that V is equal to I multiplied by R. I'm going to put this in yellow because this is the most important equation, in my opinion, for the whole electricity module. Okay, so V equals I times R. What does that mean? Well, basically, it tells us about the potential difference. So V is the potential difference of the battery, for example. This is equal to I times R, where R is the resistance, and that's basically the thing that resists the motion of charged particles moving around that circuit. The units for resistance are ohms, and potential difference has got the units of the volt, and current has the unit of the amp. So again, just be really clear, capital V for potential difference, we've got capital A for the current measured in amps. Okay, yeah. People are asking questions like, can I do mechanical engineering at university level? I mean, I did, that's what I did at university, but I haven't made videos about it before, so who knows, never say never. Okay, right, so there we go. That stuff there is all straightforward. Now, what you need to know about is the relationship between the potential difference and the current for different components. And this kind of then leads on to Ohm's law, which I'll talk about, and actually I'll talk about now, okay? So basically, Ohm's law is something that you just have to be able to state. And it says clearly over here that the current through an ohmic conductor at constant temperature is directly proportional to the potential difference across it. Okay, so basically, if you've got an ohmic conductor, what we can say is that the current is proportional to the potential difference. This is at a constant value of temperature. Now, if I is proportional to V, that means R, the resistance, stays the same. And this is kind of what we assume for things like bits of wire or even resistors. So with a resistor, it will always have a constant value of resistance. For example, it might be 10 ohms, and it doesn't matter if you've got 1 volt going through it, or 2 volts, or 3 or 4, we'd have the same value of resistance, and therefore the current is going to be proportional to the potential difference across it. And so I would say, looking at what it says in the AQA GCSE specification, the current through, I'll just highlight it here, the current through an ohmic conductor at constant temperature is directly proportional to the potential difference across it, so its resistance remains constant. And of course you can download this, by the way, if this is helpful. You can download this, this complete revision guide. I've got a link in the live chat at the very top, and I've got a link in the description of the video as well. Basically put your email address in, I'll get it emailed out to you. Okay, now talking about the relationship between current and potential difference, you need to know about these 3 graphs, and you need to be able to identify the component from the shape. Now on these graphs we have I on the y-axis and we have the potential difference on the x-axis. So these are what we call the IV characteristics of different things. So you've got I and V, I and V. Now if you've got an ohmic conductor, we said previously that the current is proportional to the potential difference, and that means we get a straight line that goes through the origin. And this is what we might see if you've got a resistor with a constant resistance. The other one that you need to know about is one that has this kind of S-shaped curve, and that is the shape that you'd expect to see with a lamp. And if you've got a filament lamp and we have a greater current going through it, there's going to be a greater heating effect because you've got the electrons knocking into that metal lattice. There's going to be more kind of energy passed onto it, so it heats up and its resistance increases. And that's why we have this shape here. And the final one is we've basically got something like this. And this is for the diode, so it allows current to go in one direction when it's a positive value, but it stops it going in the other direction. So this thing here is for a diode. How is wire an ohmic conductor if its resistance is affected by temperature? So CR7, that is an amazing question, but you've got to remember that for an ohmic conductor, we've got something at a constant temperature, and a piece of wire at a constant temperature will have a constant value of resistance. So that's why wire can also be an ohmic conductor provided it's at a constant temperature. It's only if you increase the temperature of that wire that it then stops being an ohmic conductor, because we've then got a changing temperature, so Ohm's law doesn't apply in that case. Okay, should the diode have a circle around it? I have seen lots of different exam boards and lots of questions, and there's not a consensus. Sometimes a diode is drawn like this. Sometimes the diode is drawn where there's actually a line going through the triangle. And I've also seen it where a diode can have a circle around it. Now that is correct, that's correct, that's correct. All of these are circuit symbols that I've seen published in lots of different places for diodes. And if you're not sure, basically just label it. But I would say if I was going to draw a diode, I'd draw it like this if I was in the GCSE exam tomorrow. Okay, right. Okay, let's have a look. So IV characteristics, you need to know about them. The other thing that you need to know about, because these graphs here are important, I suppose the other thing that you need to know about is the circuit that you might construct to actually measure this. Now what we do is, in order to look at the value of current and potential difference which is changing, we need a circuit with the following things in it. First of all, you need to have a power source. This could just be a cell. And then what we need is a variable resistor, and the variable resistor can be used to change the resistance of the circuit, and this means that we can change the potential difference across a component and the current going through it. We then have our ammeter that's going to be used to measure the current, and then over here in this space is where we put that test component, and we'd have a voltmeter going in parallel across it. And then up here, you'd probably have a switch. So you have to remember that circuit diagram. We've got a power supply, a variable resistor, and the variable resistor basically allows us to change the value of I and V. You've got an ammeter in series, a voltmeter in parallel, and then you've got a switch so that you can basically keep it open, only shut the switch as you're taking readings, and then you open it again, and that stops the circuit overheating. And down here is where you put in that component. So it could be a lamp, it could be a resistor, or it could be a diode in series with a resistor to limit the current going through it. So this one here is definitely one that you need to know about. Okay, right. Okay, and the resistor is an ohmic conductor. Yes, it is, yeah. Do I have any predictions for the 6 marker? Not at all. I've got no idea what could come up. The predictions, I don't think you can predict what's going to come up. You basically have to know everything. And if it's one of the required practicals, then you just need to know your method. So what kind of circuit would you set up? If you're going to be doing a 6 marker, whatever it's about, you need to think about maybe drawing a circuit diagram, or you need to draw a diagram that maybe shows the equipment and how you've actually set it up. You then need to think about the equipment that you need, including what is it you're going to use to take readings. So here you'd actually have to state we're going to use an ammeter. You'd have to state about using a voltmeter, and so make it really clear the equipment that you're using to take your measurements. Then of course you might think about the data that you're going to take, and this might include things like your just a final thing here, I do have at 7 o'clock tonight an A-level physics drop-in class, so that's going to be at 7 o'clock, so 4 hours time. So yeah, Carl, if you need to head off now, I will be going through some of the A-level paper kind of sort of briefing, get you ready for the next paper. So there'll be a quick one, fairly chilled out, because I know people have been working pretty hard. So I am doing an A-level physics drop-in class that you can book on my website for tonight. But now this is all about GCSE. Okay, right. So data, you've got to think about maybe what your control variables are. You've got to think about what is it you're changing, independent, and also you're going to have your dependent variable. So I spelled that wrong. You've also got your dependent variable as well. So maybe even if you just write this down, what is it you're controlling, what is your independent, what's your dependent, and so on. Potentially there might be a graph that you then plot, and also there might be any safety things that you need to consider. However, even just doing the basics here might get you 4 out of 6. Okay, yeah, okay, let's keep going. Another couple of graphs that you need to know about. There's this graph here, and there's this graph here. Both of them look pretty similar. We're looking at the resistance on the y-axis, and across the bottom we might be looking at the temperature, or we might be looking at the light intensity. And this basically shows how certain components behave when they're heated up or when we shine more light on them. So the one on the left is going to be a thermistor, and the one on the right is going to be our light dependent resistor. And for both of these things, basically when you've got a hotter temperature, the resistance goes down, or you increase the light intensity and the resistance goes down. And these are components that can change their resistance, and that can be really useful in real circuits. Okay, yeah. Now the other thing that you need to know about is the difference between the two main types of circuit. So if I just draw a circuit like this, I'm sure all of you know what type of circuit that is. I'm going to keep it super simple. And let's imagine we had the same components but set up in a very slightly different way. Okay, so what we've got here is a series circuit, and here we've got a parallel circuit. And what I'll do is I'm going to put some numbers in. Imagine we had a 6-volt power supply, then we've got the same potential difference for both of these. Now, in a series circuit, if we had identical resistors, these two things would share that potential difference. So there might be 3 volts across that resistor and 3 volts across that one. And of course, 3 plus 3 is equal to 6. In a parallel circuit, we've effectively got 2 separate series circuits. So for the top one, we'd have a 6 volt supply and we'd have 6 volts across that thing. And if we consider just the bottom part, we'd have a 6 volt power supply and 6 volts across that. And so in a parallel circuit, we've got the same potential difference around each loop in that circuit. If we consider what happens to the current, let's imagine we've got a certain current leaving here, and let's imagine we had 2 amps. Wherever we looked at the current in the circuit, we would still have 2 amps. So we would have the same current everywhere in a series circuit. Whereas in a parallel circuit, if we had 2 amps up here, and we had 2 amps down here, and we had identical resistors, we'd find that the current splits at this junction. We'd have 1 amp going through that, and we'd have 1 amp going through that. And as the currents join together at this junction over here, the 1 amp plus the 1 amp gives us 2 amps over there. So you need to know about those kind of simple rules for circuits. So yeah, basically, in a series circuit, the potential differences add up to make this, but we have the same current everywhere. In a parallel circuit, we've got the same potential difference across each loop, and the current splits at a junction and then adds up. Okay, all right, that all good so far? Yeah. So adding branches increases total current. Yeah, so what would happen is if you were to add more stuff to this, we basically have more pathways for the electricity to go, and that would then mean that it basically draws more current from the actual cell. Now, the other thing you need to know about is what happens to the total resistance. So the total resistance, let's imagine that's R1 and that's R2. But effectively, the more things that you have in a circuit, the greater the overall resistance. So here, for example, RT would be equal to R1 plus R2. And the more resistors you have, the greater the overall resistance. Here, though, the overall resistance actually goes down as more resistors are added. And this thing here seems a bit counterintuitive, but it's a bit like having the more routes for the electricity to move around that circuit as you add more resistors in parallel. Okay, so basically adding more resistors in parallel reduces the overall resistance. It increases the resistance for this one over here. Okay, cool. What if you had 2 resistors in one branch and 1 in another? Yeah, so that's a good question. And of course, that's relatively basic. So let's think about this other example. Let's imagine you had 1 resistor there, and in the other branch, you had 2 resistors. And imagine that all of these resistors have the same value. If you had 6 volts across that, then considering the top circuit, that would have 6 volts across it. If we consider the bottom circuit, that 6 volts is going to be split between these two things. So that would be 3 volts, and that would be 3 volts. Now the other thing would be, imagine we had a current of maybe 3 amps that's leaving this thing here. That 3 amps, it can either go through this resistor or those 2. And there's going to be a bigger resistance with the 2 resistors. So that would mean we have a smaller current going down there, maybe 1 amp, and you might have 2 amps going through this component up here. So you might have 2 amps going through there, you've got 1 amp going through there, and that means on the other side, at this junction, we add the 2 back to the 1 to get 3 amps going back into the battery. Okay, but of course, they're going to give you all of the information you need in the question. And if you wanted to work out the resistance of any of these resistors, all you need to do is use the equation that we mentioned earlier, that V is equal to I times R. So, for example, if you wanted to know the resistance of this resistor, we would say, well, this resistance is going to be equal to the potential difference across it, which is 3, and that's equal to 2 times its resistance. So that resistor there would have a resistance of 1.5 ohms. In this scenario up here, we know that we've got, again, we know that V is equal to I times R. If you want to know the resistance of this resistor, well, it's got 6 volts across it. It's got a current of 1 amp times this resistance R. So that would have a resistance equal to 6 ohms. Of course, they're like different circuits. So basically, whatever it is in the circuit, if you know the current or the potential difference or the resistance, if you know 2 of them, you can work out the third thing. Okay. Yeah. All good? Right, let's keep going. Blah, 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 blah. Okay, the next thing is you need to know a bit about AC circuits. So what we've had here at the moment is basically current going in one way around that circuit, and this is what we call a direct current. So that's basically DC, because it goes directly around that circuit. But another type of current that you need to know about is alternating current. And this is current that goes back and forwards, back and forwards. So the electrons don't actually travel all the way around the circuit, they just go back and forwards. And as they do so, they still transfer energy. Now, if we were to look at an alternating current, it must have both positive and negative values as it goes one way and then back the other way. So what you might see is alternating current does something like this. And you have to remember the following things. In the UK, the main supply has got a potential difference of about 230 volts. So that's the average potential difference in the main supply. And the frequency, little f for frequency, is going to be equal to 50 hertz. And of course, we always measure frequency in hertz, just like you do when you look at waves. Okay, so yes, so the polarity changes as it's alternating and it's changing direction. Okay. Okay, all good so far? How many people are watching? This is good. If you haven't already done so, yeah, basically if you haven't already done so, make sure that you do like the video. You can subscribe on YouTube, and also go and download these free revision notes I've got, which is basically based on the specification, and that can really help you as you're preparing for your exam tomorrow. Okay, cool. How long have we been going for? We've been going for an hour and a quarter. I reckon we'll be here for maybe another hour or so. And of course, it'll stay live on YouTube. So if you want to watch it later today, you want to re-come back and look at anything, you can do so. Okay, right. Okay, so this is an alternating current. Whereas if you had something that was just going in one direction around the circuit, that would be a direct current with that red line that I've put on there. Okay, now you also need to know, and you just need to memorize this for 24 hours, then you never need to look at it again in your life. Okay, you need to know about the wires inside electrical cables. Now, of course, most electrical cables are just one wire, but inside it there are 3 separate things. Okay, so we've basically got 3 wires inside. Now, around the wire, obviously the wire itself is going to be made out of copper. So copper has got a very low value of resistance, so we use copper to actually allow the electricity to move along it. But we've got the coverings on the outside. Now, one of them is brown, one of them is blue, so we've got a blue wire here, and then there's also one which is basically yellow and green, and that's often like stripes like this, and this one here is the earth wire. Okay, so basically the live wire is brown. We've got the blue, which is basically neutral, and the other one is the earth, which is basically safety. And what you need is, in a battery, if you think about what a real battery looks like, so you've got basically, this is like a standard AA battery. One end of it is going to be negative and the other end is positive. And if you look at the difference between the positive and the negative end, that is what we call the potential difference, because there's going to be a difference in the electrical potential between these 2 bits. Now, in a real circuit like this, if you were to measure the difference in the electrical potential between the live and the neutral, that's the thing that changes. So sometimes that difference is plus 230 volts, sometimes it's 0 volts, and sometimes it's minus 230 volts. And it's the difference between the live and the neutral that tells you the potential difference of that circuit. And we can see that it goes to a maximum value at points on the graph, then at another time it might be 0, then it's negative, then it's 0, then it's positive, then it's negative, and then it's 0. And basically, it's the difference between these two things here, which is going to give us the electrical potential, or the potential difference, inside an AC circuit. Okay, yeah, and basically the earth wire will only carry a current if there's something wrong with the circuit. So if there's a current going through the earth wire, that means it's a bad thing, or it means that something bad has happened, and that's now acting as a safety device. The other thing that you need to know about is that we have a fuse. Now, a fuse is an electrical device that can be used. Does it say anything about the fuses here? Yeah, basically a fuse is used because the fuse inside it has a small piece of wire, a very thin piece of wire. And if you have too high a current in that circuit, when you've got a big current, we get a big heating effect. And if the current is too big, the fuse wire melts. And so that means the fuse now looks a bit like this, and that wire basically melts, and it stops any more current going through the circuit. So a fuse isn't designed to stop you getting an electric shock. The fuse is designed to stop a circuit overheating. So the fuse melts to stop the circuit. The other thing is that you are not allowed to use the word electrocuted. Okay, that word there is a banned word. Instead, you need to use the word, if it does come up, of electric shock. The reason being that if you maybe had a case where the live wire was touching the outer metal case and you touched it, you would get an electric shock. That's what would happen to you. Electrocution is a bit like execution. So think of this as like an execution. So that's when you basically use electricity to try and kill somebody. So think of electrocuted as executed, and don't use it. So we're not trying to harm people. Instead, in your exam, you should use the word electric shock. They might let you use the word electrocuted, but you shouldn't say somebody's been electrocuted. You should say that they've experienced an electric shock. There we go. Right, moving on. Let's keep going. There are now some more equations that you need to know about. Now, of course, we know that the power is equal to the energy transferred per unit time. We did that earlier looking at at energy. But now we might want to think about the power in a circuit. So let's imagine we've got a circuit where we've got maybe a cell and we've got a resistor like this. We've also got a bigger circuit that's got a big battery like this, and we've got the same type of resistor. And let's just put some numbers in to kind of see what's going on. Let's imagine that's 1 volt and this one here is 6 volts. And that has a current equal to 2 amps. And this one here has got a current equal to 4 amps. Which one of these things is going to be transferring more energy every second? Well, I would say, first of all, probably the one with a greater potential difference will be transferring more energy. And also, the one that's got a greater current is going to be transferring more energy as well. So that means the electrical power is going to depend on two things. It's going to depend on the size of the potential difference, which is V, and it's going to depend on the size of the current, which is I. And so this is where we get this equation that says P equals V times I. So if you want to know the power of one of these, you basically multiply the two numbers together. So this one here would have a power of 1 times 2, so that would be 2 watts. And this one here would be 6 times 4, which is 24 watts. And that just means that this thing here transfers 2 joules every second. This one is transferring 24 joules every second. Okay, let me just get rid of a few people. Okay, so yeah, power is the energy transferred or the work done per unit time. We can also calculate it like this. But I said previously that V is equal to I times R. That one there, the most important equation in physics for electricity. And what we can do is we can replace this V with I times R. So we could also say that the power is equal to I times R, which is V, multiplied by I, and that means the power is equal to I squared R. So that thing there is also really important. And it's for this reason that we use transformers in the national grid. So in the national grid, what we have, and I probably should have mentioned this previously, is you've got your power station, you've got your step-up transformer, your step-down transformer, and you've got a house over here where you are sat there watching me on the live stream at the moment. So this thing here is where we're going to generate some electricity. And then we've got the wires that go here. We've got some pylons. It's quite hard to draw a pylon. And of course we've got the wire going through the pylons back down here. Now in the national grid, which is basically this bit to this bit, that's the grid of all the wires and pylons and things like that. We've got a step-up transformer and we've got a step-down transformer. Now, the important thing here is that we always have the same amount of energy, and so we know, of course, that if you had a certain power, let's imagine we had a power of 1,000 watts, we'd have 1,000 watts here and 1,000 watts down there. So we're always going to be transferring the same amount of energy, but we know that the power is equal to V times I. Now, over here, we might have a certain value of potential difference, and we've got a certain value of current. And what we do with the step-up transformer is we step up the potential difference. So we might step up V to a massive number. And I think somebody said just here in the chat, 400,000 volts. Yeah, so basically we have a really, really high value of potential difference. And then what we do at the other end is we step it back down to a more reasonable value and a kind of current that's going to be useful in the house. And so here, that V might be 230 volts if it's like the AC supply in the house. But of course, the power is equal to V times I. And if we're going up and increasing the value of potential difference, that means to compensate for that, we've got to make the value of I really small, because V times I must be still equal to the same number. So if you had 100 volts times 10 amps, you then go to maybe 1,000 volts times 1 amp. And the whole point here is that what we do is we increase the potential difference and we decrease the current. And that means if we've got a smaller current, we're going to have a much smaller value of energy loss in the cables. So if we were to maybe reduce the current by a factor of 10, we'd reduce the power loss by a factor of 10 squared, which would be making it 100 times smaller. There we go. Okay. Yeah, right. So increasing potential difference decreases the current. Yes, it does. Game of 4862 in a transformer, because you've got the same amount of energy transferred in as you've got out. Power in is equal to power out, and that's why we step up the potential difference, and therefore we have to decrease the current. And that's why we do it, because if you didn't have a high value of potential difference and a low value of current, then we'd have too much heating losses for the fixed resistance of those wires. Okay, right, let's keep going. So you need to know about that equation. The other equation that you need to know about, well, actually it basically repeats itself. It says here that energy transferred is equal to power times time, but basically that equation here that it gives you in the specification is just this equation up here, where we just rearrange it to say that E is equal to P times T. So the energy transferred is equal to the power multiplied by the time. And the other thing here is we can also say that the energy transferred is equal to QV. So Q is going to be the charge transferred, and V is the potential difference. And don't forget that earlier we said that charge is equal to current times time. And in actual fact, for those of you who kind of like physics, if we were to put this back in here, we could say that the energy transferred is equal to ITV, because you've got I times T times V. But of course the power is equal to V times I. So we could also write the energy transferred as the power times time. And of course, that's just the equation that we had over there. So you can see with lots of physics, the equations all sort of just like mash up together, and they all kind of, you can do really interesting things with them. Okay, right, so yeah, basically that's why the national grid is so important. Now the next section is something I'm going to do in blue, and the stuff I'm doing in blue is for triple only, and it's going to be triple sometimes separate science. Okay, so basically this is only for those of you who are doing triple. By the way, in the chat, let's see how many people are here. So we've got in the chat at the moment about 136 people watching. Can you, all of you, let me know, are you doing combined trilogy or are you doing triple physics? Can you all let me know? So let's see, we've got Ultra VJ Legends doing triple, Racer27 doing triple, Victoria doing triple, Triple Gang says Relux, Gamer, RC, it doesn't matter. Okay, so we've got Sulo doing combined trilogy, says Henry, Grog doing triple physics, combined, triple combined, triple combined, triple combined. Basically, everything I've done so far is the same for everybody. The next bit here, if you're doing combined science, go out and like get a cup of tea or a coffee or something like that. We're just going to have a look at static electricity, which is the thing that triple science need to do, but not everybody. So if you're doing triple science, you need to know about static electricity and a little bit about maybe charged fields. And then apart from that, the next bit is going to be the same for everybody. Okay, so yeah, combined, triple. We haven't finished combined, by the way, Aisha, we haven't finished it. We're just doing a little bit more for 5 minutes, and then we're going to come back. And after this, what we're going to look at is we're going to be looking through the particle model and gases, and then we're going to finish looking at atomic physics. So just have a little break if you are doing combined. Right, let me just go and open the window. It's getting hot in here. Okay, all right, okay. Right, so, okay, triple separate physics. So let's have a look at static electricity. Now, what we've been looking at so far is where you have electrons, these small particles which are moving around the circuit. Now, if they're just moving one way round, that's a direct current. If you've got electrons which are moving back and forwards, and they're basically just oscillating about the same point, that is when you've got an alternating current. But we can also have things where you might have lots of charged particles that aren't moving at all. So you might have lots of negative particles over here, and you've got lots of positive particles over here. So this could be, for example, a load of electrons which have been separated from some metal atoms, and we've now got maybe the positive metal atoms left over here, and we've got the negative electrons over here. Now we've got charges, so positive and negative, but they're not moving, and therefore they are static, and this is why we talk about static electricity. However, the negative things will be attracted to the positive things will be attracted to the negative, and there's going to be a region in the middle where these things experience a force. And so what we have between the two things is an electric field. So, yeah, right. Okay, so so basically this is what we talk about with static electricity, and you need to think about how this can occur. The common example is basically if you have an insulator and you rub it on another insulator, we then get the movement of charged particles, and it's often the electrons which are transferred from one thing onto the other. So this could be your face here, and that's your hair, and you get a balloon, and you rub the balloon on the head, and basically your hair is an insulator, we rub another insulator on it, and what this will do, it will transfer charge from one thing onto the other. So maybe the balloon becomes negatively charged, and that means, again, this is you over here, and you're holding the balloon near to it. This has got negative charges on it, and now your hair basically kind of points towards it because your hair has an overall positive charge because it's lost electrons. So a hair sticks up or it points towards the balloon. So basically a couple of insulators rubbed on each other, and there are loads of examples. It could be people going down a slide wearing like nylon trousers. It could be a polythene rod that's rubbed with a duster in a science lab. Lots of examples can come up in exam questions about this. Okay, so what we have here are the separation of charged objects, and I guess it's going to be a non-contact force. So this thing might be attracted to that, that's going to be attracted to that, and we've got this non-contact force between the objects. Yeah, then of course, describe evidence that charged objects exert forces of attraction or repulsion when not in contact. We kind of know this, I guess, even down to maybe thinking about what's going on inside the atom. So imagine you had a positive charge, like a proton, and you had a negative charge, like an electron. There's still going to be a force of attraction between these two things as the electron is going around in its kind of circular path inside the atom. There's going to be a force of attraction even though it's acting at a distance. And then finally, an electric field. So objects have an electric field around it. Now, an example that hopefully you've all had a go at is looking at a Van de Graaff generator. So a Van de Graaff generator is a big steel dome. This is kind of mounted on a thing where there's this rubber belt that's basically going up and around. And what you have is a rubber belt that's basically going across a piece of plastic. So you've got two insulators which are rubbing against each other. And then maybe this makes the top of this a positive charge. Now, if you put your hand near to this, I'm not very good at drawing hands. Imagine that's your arm and you put it towards it. You might feel a few tingles in your finger. And if it goes really close, there might even be a spark. And that's because in the region around this positive charge, there's going to be an electric field. Now, when it comes to drawing the electric field, which is a standard exam question, you need to basically use a ruler and you need to use a pencil. So you've got these field lines, and I'm going to draw 8 field lines here, and these represent the direction of the electric field. And the electric field near to something positive is going to be moving away from it, because the direction of an electric field is the direction that a positive charge would move. So imagine you had a proton and you put the proton here, that would be repelled from the electric field here that's positive, and it would move away. Now you can see as well that near the surface the field lines are closer together, and further away the field lines are further apart. So what you have is a strong field at the surface, and then it's weaker the further away you go, which is very similar to what happens with a magnet, where if you think about, and this is very much what you're going to be doing in paper 2, if you have a magnet, you can draw in the magnetic field lines like this around it, and basically where the field lines are closer together, we have a stronger magnetic field. Where the field lines are further apart, the field is weaker. But of course, this is an electric field, so the strength of how many lines you have together shows if it's strong or if it's weak. Okay, yeah, let's see what people are saying. How are you supposed to know which insulating material loses electrons and which one gains it? You basically can't tell. It'll say you've got basically material A is rubbed against material B, and so maybe that's just like rubbed up and down. You can't tell based on if it's polythene or whatever it might be, but what you will be given then is enough information in the question that allows you to work out what their charges are. So it might say, for example, as object B is rubbed on object A, electrons are transferred from B to A. So if electrons are transferred from B to A, that's going to mean that this thing becomes negative, and this thing here, because it was neutral initially, now has positive charges on it. And of course, the danger with static electricity is if you put something nearby, like your finger. Okay, so that's your finger. If you put your finger or something which can conduct near to this, there might then be a bit of electricity that jumps from one to the other, and that's when you then might get an electric shock, as we basically get a small current or even a large current flowing as it discharges through you. Okay, and so basically if you've got a conductor, what this will do is a conductor near to one of these things will earth it, and basically if you put your finger near to this, or if you put a conducting rod, what that's going to do is allow these charges to flow to earth. This then becomes neutral, and what we've done is we've discharged it or we've earthed it. Okay, and that's all a spark is. That's what lightning is. So the other night we had some amazing lightning storms. So we basically had clouds, and you've got the ground. And imagine that the cloud is rubbing against other clouds. We're going to have basically insulators in a very simple thing, basically rubbing against other insulators. This then has a massive negative charge on it. And of course, negative things don't like being near other negative things. They're all repelling each other. And then if you've got something like a church steeple with like a thing on top, that might be the highest thing around. And as this discharges, we get that kind of lightning strike, and it basically hits the high thing. If it's somebody playing golf, if it's a metal spike or something, it's going to hit that. It could be a tree, and then it discharges. So that's all that lightning is. Okay, so that bit there was all that you need to know really about static electricity. And now, combined people, you can come back in the room. We've got 2 more sections to go. So we're going to look at the particle model and gases first of all, which is basically chemistry. And you've already done it because you've already done chemistry paper 1. A few things you need to know about. And this is where you need to realise that your maths teachers haven't been teaching you well. The first one is about density. Density has got the symbol rho, and it's equal to the mass, which is small m, divided by volume. That's how it should be seen. In maths, though, they often say that, and this is, by the way, incorrect, density is equal to mass over volume. You might see that in the maths classroom. So basically, have a word with your teachers, tell them they're not doing the right thing. That's not good physics, so I'm going to ignore that. This is what it should be like. Density has got the symbol rho, which is this curly p, and it's the mass per unit volume. And so we might think about the density in kilograms per cubic metre, or sometimes grams per cubic centimetre. Okay, there we go. And mass should be lowercase, volume is capital. Cool. Hope that helps, Katsui. Okay, then of course we've got the particle model, which is basically the particle model means that we basically ignore chemistry. Now chemistry can get a little bit tricky because you've got like O2, which is like 2 oxygen atoms bonded together. You've got all these kind of crazy gases. There's going to be van der Waals forces between them. You've got different reactions. We ignore all of that, and in physics we make it super simple, and that is a particle. There we go. And of course what we can then think about is how the particles might behave next to other particles. So you might have something where you've got a few particles moving around, colliding maybe with the edge of a container, and we've got a gas. You've also got particles that basically are going to be close together in this kind of random arrangement. It's supposed to be random. And this is where we have a liquid that's going to kind of take the shape of the bottom of a container. And then we've got a much more regular structure where the density of a solid is the same as the density of a liquid, but we've got a much more regular kind of layout, and this is where you've got a solid. So you've got a solid, a liquid, and a gas. You need to know how we go from one to the other. So we've got solids, liquids, and gases. As you go from a solid to a liquid, what we're doing is we're melting. A liquid to a gas is boiling. A gas to a liquid is condensing. A liquid to a solid is freezing. And then also you can go from a solid to a gas, which is sublimation. And there's also one where a gas becomes a solid, which is deposition. So you need to know about those changes of state. And I think some good definitions from people like Racer27 in the chat. Somebody says, A-level student here, I miss it when physics was this simple. This is still the model that we use in A-level physics. We just kind of name the assumptions about an ideal gas, but we still have the same assumptions. So A-level physics isn't much trickier really. I would say that the graph that I think is really important is this one over here. Okay, this graph here shows the temperature of something, and it shows the energy inside it. And what you have here at low temperatures, where the particles don't have much energy, this is where you've got a solid. Then we have something turning from a solid into a liquid at a constant temperature. So here you've got something melting, and it's important to remember that when you've got a phase change, it happens at a constant temperature for a pure substance. And then you've got a liquid turning into a gas, again at a constant temperature, and that's what we have on this part over here. And of course, as you have something which stays as a solid, or it stays as a liquid, or it stays as a gas, we know of course that the energy transferred is equal to mc delta theta. Okay, so basically as the energy increases, the temperature of that object also increases, which is when you've got something that stays in that same state. Okay, right, yeah, cool. Somebody says they've just had A-level paper 2 today and they're unwinding with more physics. I think that, yeah, for something like this is kind of quite relaxing, having done a real A-level. Yeah, for this, we've got the same mass. And that's another important thing to say, is that when you go from one of these to these to these, in this model, what we have is a physical change, and that's where all we're doing is we are changing how those particles are arranged. So it's not a chemical reaction, so it means that it's completely reversible. So when you take the liquid and you freeze it, it re-becomes a solid, and you've got this reversible change, and there's going to be no change in mass. All we're doing is we're adding energy to something, the particles gain energy, and therefore they change the way that they're arranged. Okay, cool. Right, so there we go. Solids, liquids and gases. And then you've got a bit more here about internal energy and energy transfers. In the specification as well, it does say the equation that you saw when we looked at energy at the very beginning. So the change in thermal energy is equal to the mass times the specific heat capacity times the change in temperature. Okay, the other thing that you need to know is, although we know that there's going to be a certain change in energy as something changes in temperature, you also need to know that when we have a change of state, we can say that E is equal to mL, where L represents the specific latent heat. Now before C stands for the specific heat capacity, the word specific just means per kilogram or per unit mass, and so L is specific latent heat, and that's the amount of energy required to change the state of 1 kilogram of a substance. So this happens at a constant temperature, but you need to know what that means. And I think that's basically it for the sort of the model of solids, liquids and gases. The next thing that you need to know about is you need to know a little bit more actually about gases. And basically what it says here is that if you've got particles in a gas which are moving around and they're going to be colliding with the walls, you need to know that there's a relationship between the pressure and the temperature of a gas. And what we can say is that the pressure is proportional to the temperature. So what that means is if you double the temperature, what's going to happen to the pressure? The pressure doubles. And that works if you've got a constant volume of a gas. So you think about, imagine you've got like a can of deodorant that's got some pressurized gas inside it. On a hot day, that's going to be at a higher pressure than on a cool day. Because on a hot day, the particles inside, they're going to be moving around quicker, and that means if they're moving around quicker, they're going to collide with the container walls with more force, and also we know that pressure is equal to force over area. So something that you might have seen before you did GCSEs was that pressure is equal to force over area. And if you've got something which is hotter, the hotter an object is, the faster it's going to be moving. If it's moving faster, it's going to collide with the walls of that container with more force. And if you've got more force over that certain area, we're going to have a higher pressure. Okay. Gamer 4862, how much harder is A-level physics and GCSE? I would say it's not a billion times harder. Thank you to people saying that. It's more challenging, but to be honest, A-level biology, A-level chemistry, A-level maths, A-level psychology, A-level sociology, all A-levels are going to be much more, there's a lot more content than you did at GCSE, but then of course you have to learn less of it because you're only doing 3 subjects. You're not having to learn 8 or 9 subjects like all of you are at the moment. Okay, so that's a little bit about pressure. Now the next bit I'm going to talk about is going to be only for those of you doing triple, because you don't just need to know about pressure and temperature, you also need to know about pressure and volume. And what this means is, imagine we've got that sample of gas that's got some particles inside it, and what we do is we take that gas and we basically make it smaller. So what's the link between the pressure of the gas and the volume inside? Well, what we can say is that the pressure is inversely proportional to the volume. So what that would mean is if you were to halve the volume, we'd double the pressure. So let's imagine this had a pressure of 101 kilopascals, and we halved the pressure to like 50.5 kilopascals. Imagine initially, sorry, that might be the pressure. No, ignore that. Imagine we initially had a volume of 1 cubic metre and we halved the volume to 0.5 cubic metres. Now, initially the pressure might be 101 kilopascals, which is actually the atmospheric pressure. If you halve the volume, what we do is we double the pressure, so the pressure might now be 202 kilopascals. Okay, and we measure pressure in pascals, where 1 pascal is the same as 1 Newton per square metre. Okay, so this is the unit that we measure pressure in. Okay, so this means that if you were to halve the volume, we double the pressure, and that's why pressure is inversely proportional to volume, or we can say that the pressure times the volume is equal to a constant value. Okay, and that's what it says here, and this is something called Boyle's law, and it basically says for a fixed mass of gas at a constant temperature, the pressure is inversely proportional to the volume. And a thing that I think is really useful is if you knew the initial pressure and the initial volume, you could work out the final pressure or the final volume. So this one here is like an additional equation which I think is massively useful. So it's not in the data book, but I think this is really useful, that P1V1 equals P2V2. So if you knew the initial pressure and the initial volume, and you knew the final volume, you could work out the final pressure. Okay, all good so far? Right. The other thing that you need to know about if you're doing triple is basically if you do work on something, then it increases the internal energy, which causes the temperature to increase. So basically this means if you do work on a gas, for example, you're compressing it, maybe you're doing work with a bicycle pump, if you do work on it, that means you're transferring energy to the gas. And if you're transferring energy to it, this might then make the particles have a greater value of kinetic energy. So if the particles have got a greater kinetic energy, that means that they're going to have a greater value of velocity. And if they're moving quicker, that means the temperature of those particles goes up. So there we go. I think that's basically the last bit. So the last statement that you need to know here, if you're doing higher tier triple physics, explain how doing work, which means that you're transferring energy by a force acting over a distance. It increases its internal energy. which means it's going to cause its kinetic energy to increase of the particles. So the particles are moving quicker, so they've got a greater temperature, and therefore that might then also mean that the gas is at a greater pressure. All right, the last bit then is going to be suitable for everybody, and we're going to be looking at atomic structure. Sorry, I've got so many bits of paper here, it's quite a lot. So atomic structure is basically largely the same as what you've already done in chemistry paper 1. Actually, if you bear with me for 2 minutes, I'm just going to go out and get a drink to kind of keep my voice working beautifully. But I'm just going to put here the things you need to know, and I think it's important to see how a lot of this is identical to what you've already learnt and revised for chemistry paper 1. So I'll be back in about 2 minutes with a drink. Okay, I'm back. Got myself some Ribena. Let's keep going with the last bit. Yeah, I am here. Yeah, so I went to get a drink. I think I've been talking for like a couple of hours. So I guess it's a 2-hour stream so far. Probably maybe another half an hour for the last bit. Has that really been 2 hours? Yeah, so my voice is getting a bit dry. Okay, basically, this is what we need to know about for the physics part of the course. And really, in the last module, everybody needs to know the same thing. It's only the very last bit which goes into a bit more about fission and fusion. That is for those doing triple science only. So most of the first part is the same. And you have to remember this number. Now, just like I said earlier, you need to remember the frequency, 50 hertz, and the potential difference, 230 volts of the main supply. You need to know the number here, that if you've got an atom, the radius of an atom is about 1 times 10 to the minus 10 meters, and the nucleus, so the radius of the nucleus is going to be about 10,000 times smaller. And so if we think about what this means in terms of using standard form, 10,000 is 10 to the 4. And if you've got something which is 10,000 times smaller than 1 times 10 to the minus 10, that's going to then be 10 times 10 to the minus 10 divided by 10 to the 4, which is about 1 times 10 to the minus 14. So basically that's about the scale of the nucleus, and that's about the size of the atom. So you must remember that the size of the atom is about 1 times 10 to the minus 10. The size of the nucleus, depending on the kind of atom, is about 10 to the minus 14. Okay, right. The other thing is that you know that the mass of an atom is concentrated in the nucleus, made up of protons and neutrons. So you've got protons and you've got neutrons that make up the nucleus. And then around this, you've got electrons in shells. And of course, that's the stuff that you've done lots of work on in chemistry. Okay, so you've got different electrons in shells. And the rest of it is pretty much identical to what you did in GCSE chemistry. You do need to know about an isotope. So an isotope is basically something where you've got the same number of protons, and it's the number of protons that actually identifies what type of element we have. So carbon will always have 6 protons, but you're going to have a different number of neutrons. And that's often why we have things which are radioactive, because if there's not quite the perfect number of neutrons to protons, the nucleus is unstable, and therefore it might want to decay to become more stable. Okay, right. Yeah, these ones here, both of those in meters for those values here. So 10 to the minus 10 meters for the radius of an atom. The next thing then is you need to know about the different models that we've had of the atom over time. Again, this is what you saw in chemistry. So first of all, initially we thought of atoms as basically being tiny spheres which are indivisible. We then went on to the plum pudding model, which is basically where you've got negative charges embedded in a positive sphere. So this is very much like raisins in a Christmas pudding, or at the time they called them plum puddings. Then we went on to the alpha scattering. So alpha particles are radioactive particles. They're positive, and what they were basically fired at gold leaf. And then we found that there's basically this model of the atom, which basically had a dense positive core surrounded by this field of electrons. And of course, with the alpha scattering, some of the particles just went straight through, some were deflected a little bit, and some of them were actually deflected quite a lot. And the only way that we could have something which would bounce back from the nucleus would be if we had something which was also as positive as the positive alpha particles as well. So alpha scattering basically said that the atom is mostly empty, and also there's a positive core where most of the mass of the atom is actually stored. So there we go, that stuff there, you've already done a lot of that in chemistry. And this part here that comes up in the specification, it's just quite a lot of stuff that you just have to remember. Yeah, right, there we go. And then of course, then we went from the model where we just had a dense positive nucleus. Later on, we realised that we actually had positive things and neutral things in the middle. But that wasn't really till about the 1930s. And also, we've got distinct energy levels where electrons can exist, and electrons can actually move between energy levels. If they absorb electromagnetic radiation, they can go up, or they can come back down an energy level as they give out electromagnetic radiation. Okay, right, yeah, so basically Dalton, J.J. Thomson, Rutherford, Bohr, Chadwick, Bracer 27. Yeah, so basically J.J. Thomson was about the electrons, and then we had like Rutherford doing the alpha scattering thing. The Bohr model had the things in different shells, and then the Chadwick basically discovered about the neutrons in the 30s. Okay, now what's more interesting though is that we have some isotopes which are not stable, and in the nucleus there's either too many protons or too many neutrons. And what the atom does is it gives out particles to try and become more stable. There are basically 3 different types of radiation. We've got alpha, we've got beta, and we've got gamma. And for these, you need to know about some of their properties. So first of all, alpha radiation is 2 protons and 2 neutrons. And because of that, it's basically got a charge of +2. Where if we say a proton is +1, this is made out of 2 protons, so it's got an overall charge of +2. Beta is going to be an electron, and it's an electron that's emitted from the nucleus, and all of these things come out of the nucleus, which is why we have nuclear radiation. And so this beta particle is basically a high-speed electron, so it's negative and it's got a charge of -1. And gamma is part of the electromagnetic spectrum, so it's just a wave of energy, and therefore it has no charge. Now, all of these things here, they have a certain amount of energy, and when they collide with other atoms, they can knock electrons out of those atoms and turn them into ions. So these things here are all types of ionizing radiation. So that means gamma, the energy can be absorbed by the electrons in the outer part of an atom, it ejects the electron, and then we're left with a positive ion. An alpha particle can come along and grab hold of a couple of electrons. So all of these are things that we need to know about. Do you need to know about the mass of alpha and beta? Yeah, so the mass of this one here, if this is the charge Q, the mass of them, well, this has got a relative mass of 4. If we say that a proton or a neutron has a mass of 1, this one, the beta, it's got a mass of about 2,000ths of that, because it's the same as the mass of an electron. So about 2,000th or 1,856 or something, 1,860, it's got a much, much smaller mass. And the gamma has got no mass at all. Now this then tells us other things. So basically this one here, because it's got a massive charge and a massive mass, it is highly ionizing. This one is medium and this one is low, if we think about how much they can actually damage other cells. So alpha is highly ionizing because it can go along, smash lots of different electrons out of lots of atoms, cause lots of damage, whereas gamma is much less ionizing. Also, the other thing we need to know about is their range, and also how well they can penetrate other things. So alpha is going to be very short range, beta is medium, and gamma is very, very long. And so what that means is alpha is stopped. We've got this. So beta is high-speed electron emitted from the nucleus. Gamma is electromagnetic wave. Alpha is a helium nucleus. Yeah, perfect. Okay, so the range of this is really short. And it might just be stopped by a couple of centimetres of air. Beta travels a little bit further in air, but then of course it can be stopped by something like a thin sheet of aluminium. And gamma has got a massive range, and it will go through lots of lead and concrete and water. You need a really big, thick thing to actually stop that. So they've got a different kind of range. And then I guess if we think about penetration in terms of how far they go into materials, what kind of stops them? Well, alpha is stopped by paper, beta is stopped by aluminium, and gamma will eventually be stopped by lead. Okay, Yeah, alpha, good question there in the comments. Alpha has a short range because it's very, very large. And therefore, if you think about it, it's quite big compared to these two other types of radiation, but it's going to be quite small compared to large air molecules. And that means there's going to have lots of collisions with these large air particles, whereas this one here is a lot smaller, so it can sort of just work its way through. Okay, so we've got these different things here. The other thing you need to know about them is what happens with nuclear decay equations. So if you think about what happens, let's imagine we start with element X that's got 50 protons and it's got 120 protons and neutrons in total. So this is just a made-up element. If this decays by alpha emission, and an alpha particle is the same as a helium nucleus, so it's got 2 protons, and of course it's got 2 neutrons as well, so the number at the top is 4. Effectively what we've done is we've taken 2 protons out of the nucleus. So we might have had 50 protons there before, we've taken away 2, and now we've got 48. And that means we're going to have a new different type of element. So we started with X, we might end up with element Y, again completely made up. And the other thing is if you started with 120 things in the nucleus, we've got 4 of them that have been ejected, that leaves 116 left. And so this is a kind of typical nuclear reaction, but it's no harder than anything you do in chemistry. All we're doing is we're conserving the numbers. So just in the way that you might balance a nuclear, or you might balance a chemical reaction, all we're saying is that the number on the left at the top, 120, is the same as the number at the top on the right. So you've got 120 there, and you've got 4 plus 116. And the numbers at the bottom need to add up to the same on both sides. So you've got 50 there, and we've got 2 and 48, so we've got 50 there. So we've basically conserved the kind of overall number of protons and neutrons. Okay, right. The next thing is, this is alpha decay. If you've got beta decay, this is when you have a high-speed electron ejected from the nucleus. So let's imagine we have the same thing that we start with. Obviously, the same atom wouldn't give out 2 different sorts of radiation necessarily. If you've got element X and it gives out a high-speed electron, so this is E, it's got no protons and neutrons, but we actually give it the number -1. Now, the reason for that is the electron comes from a neutron that turns into a proton and an electron. So what happens is that the neutral neutron makes a positive proton and a negative electron. So inside the nucleus, we've got a neutron turning into a proton. Now, what that means is if we had 50 protons before, and one of the neutrons has turned into a proton, we now have 51 protons in that nucleus, but we've still got the same total number of protons and neutrons. So we started with 120, we end with 120, just one of them has turned from a neutron into a proton. So this might be a new element Z. And so this is what happens when you have electrons being emitted, the beta radiation. Okay, and then finally, gamma, maybe you start with gamma, where you've got an unstable nucleus, and this gives out one of these gamma rays, so that's the symbol for a gamma ray. It's got no protons and neutrons, so it's got a 0, 0 number, and that means we start with 50 protons, we end with 50 protons, we start with 120 nucleons, we end with 120 nucleons, and all we've done is we've got rid of this bundle of energy. And it's basically because the actual nucleus had too much energy, and so in order to kind of become more stable, it ejected a little packet of energy over here that we call a gamma ray or a gamma particle. Okay, and there we go. That bit there is just some of the nuclear equations. The next things we're going to look at is looking at half-life. Now, if you look at the number of atoms over time, what you might see is this is the number of atoms that we have, and over time, the number of radioactive nuclei decays, and we get this kind of curve here. Now, this is what we call an exponential decay curve, and it means that over the same time period, the number keeps falling to half of its original value. So let's put some numbers in. Imagine we started with 120 particles. After a certain amount of time, the number left drops down to 60 particles, and this time here, T, is what we call the half-life. So the half-life is the time it takes, and it says here, and this is just a definition you need to know about, and also somebody's got it there in the chat, half-life is the time taken for for half the number of radioactive nuclei in a sample to decay. So half-life, the time it takes for the number of nuclei of the isotope in a sample to halve. Okay, now what that means then, it goes from 120 down to 60. If it goes down from 60 down to 30, this takes, again, the same amount of time. So let's imagine the half-life was equal to 50 days. Then the time it takes to go from 60 down to 30 is going to be another 50 days. So that's going to be 100 days in total. And if we go from 30 down to 15, this is going to halve from 30 down to 15, and it takes another 50 days. So now that time there would be equal to 150 days. And if we went from 15 down to about 7.5, that would take another 50. So what we do is we half and we half and we half, each one taking the same time period. Now, something I've seen before, which was previously one of the hardest papers that I've seen, was it gave you a graph like this and it asked you to look at the activity. Now, the activity of a sample is something that is measured in the unit of the becquerel, and it basically tells you the number of decays per second. And so the activity is going to be equal to the change in number over a certain amount of time. So the activity of a sample tells us how many of these things are decaying every second. And you can actually work out the activity from one of these graphs by drawing in the tangent to the line. So this is very much a higher physics skill. If you draw in the tangent and then you work out the gradient of that line, the gradient of the line is going to give you the activity of that sample, which I've seen before come up once or twice over the last few years with AQA questions. And so if you did have to work out the activity of a sample at a different time, when you had a graph like this and the number of isotopes, you would draw in a tangent to that line and then work out the gradient. So the change in Y value divided by the change in X value. Yeah, so it's the gradient and not the area under the curve. The next thing I want to talk about is the difference between contamination and irradiation. Now, the two things are completely different. For example, you can be irradiated by a load of radiation and you will not become radioactive. You might have some damage to your cells, but you wouldn't necessarily become radioactive. Contamination, though, is when you're covered in that thing. And so I guess imagine, there's probably going to be some good analogies about this. Yeah, so basically contamination is when a radioactive sample is on or within you. Okay, and so basically this is when some of the radioactive isotopes might get onto your skin, or you might ingest them, which means that you eat them or you drink them and then they're inside your body. Contamination is bad because if you're contaminated, you're constantly having radiation damaging your cells. But irradiation means that you're only exposed to that radioactive material for a very short amount of time. Okay, so contamination is like a stain. Yeah, I think that's a nice thing. So irradiation is the exposure to radiation, but without leaving the object radioactive. Yeah, exactly. It's a bit like, imagine you put your hands near to a fire. So imagine you went out in the garden, there's like a big fire or a barbecue or something like that. If you put your hands near to the fire, you can feel the heat energy being transferred off it. So there's this kind of radiation and there's this infrared radiation and you can feel the heat. As soon as you walk away from the fire though, you're stopping being exposed to that heat. And so although you might have been irradiated by the heat from the fire, as soon as you move away, you're absolutely fine. However, if you got a piece of like maybe it's some wood or some coal, imagine that kind of dropped onto you and it left like a stain with a kind of sort of blackened charcoal that you might get from a fire. Hopefully it's not too hot. But imagine you had that stain on you. As you walked away from the fire, you would still have that stain on you. And effectively that's a bit like you being contaminated. So it's a bit like kind of putting your hands near the fire, and as soon as you take your hands away, you're not feeling hot anymore, as opposed to if you put your hands into like the ash at the bottom, that would then contaminate you, because even when you walked away from the fire, you'd still have it on you. Is that okay? Yeah. Right. Irradiation can be wanted or it can be unwanted. It depends on the scenario. So this is why we often use radioactive things, because basically sometimes we want to expose things to radiation. For example, you could use gamma, which is highly penetrating, and imagine you had a gamma source up here. So this is your radioactive source, and basically this thing here is pushing out gamma rays down here. If you put a medical instrument in this, so here you've got some like scissors that you used for operating on somebody, the gamma radiation might kill all of the microbes on this, and you've then sterilized it. You then take it away and you've got completely sterile equipment, but it's not radioactive, and then you can use that for surgery. Okay, cool. Right, but irradiation can be dangerous, but it just means that once you leave that environment, you're not still radioactive. Okay, and then the last bit is, the last bit of this thing here is only for people doing triple science. So the last bit of the course here, and again this is just a very kind of quick bit of revision, is looking at some of the hazards and also things like background radiation. So you've got to realise that you are all being irradiated, even if you're not contaminated. There's this background radiation that all of you are exposed to, and there's going to be man-made stuff and natural. Now, natural background radiation, some of it's coming from space, and this is cosmic rays, often highly energetic particles which have been released by the sun. You've got the rocks underneath us. So there are radioactive rocks underground that give out things. We also have, and I guess the rocks often release radon gas, and this radon gas can build up in areas which aren't ventilated in some buildings. But there's also man-made sources of radiation. So this could be from really old nuclear testing that maybe happened a long time ago and it's just up there in the atmosphere. It could come from medical uses. For example, if you've had a scan at a hospital, there might be a medical tracer that you've ingested. And of course, there might be things from like nuclear accidents and so on. So there's going to be a whole range of background radiation. The other thing is that there's going to be some hazards associated with real radioactive material. And one of these is that they've got a very long half-life. So if we were to look at some things, we might find that the half-life might be 1 million years. And that means if we have something which is maybe produced in a nuclear fission power station, there might be daughter products which are left behind, which have a very, very long half-life. And that means even though we're only using them now, how do we dispose of this material, which is going to remain radioactive for the next 1 million, 2 million, 3 million years? Okay, yeah, so basically there's that. And of course the other thing is that there can be some benefits. So although there are bad things about radiation, there are some benefits to using it. So one way might be that this is you, and there's something wrong with you. So that's supposed to be you there. Okay. What we can do is we can give somebody a radioactive tracer, and maybe they ingest it in, and then it kind of basically goes into their blood or it goes through their digestive system. And if you've got something which is giving out certain types of radiation, we can maybe detect where your body isn't behaving as it should, or it might be that there's a radioactive tracer that's been bound onto something which is then concentrating in cancerous cells. So there can be some benefits to using things which are radioactive. And so one of the big uses of this is in medical physics, and we can use medical tracers. Now, of course, there are going to be some pros and cons. The con is that you are being exposed to a radioactive material, but what we try and do is we try and minimise the risks. For example, we might use something with a very short half-life, and we're going to use the lowest dose possible. But of course, the advantage is that could then tell us where maybe you've got some cancerous cells or there's some other problem with your body, and that then allows it to be treated so there's no long-term health risks. So a lot of these ones here, it's kind of going to be like pros and cons that you get. The next thing is about fission and fusion, and these two things are very, very different. Okay, so again, this is for only people doing triple science. You've got nuclear fission and you've got nuclear fusion, and it's worth just emphasising you've got 2 S's in fission and 1 S in fusion. Okay, fusion means that you join things together, and fission, like a fissure in a rock, basically means that you break things up. Now, fusion is a kind of thing that happens in all stars, in the very, very centre. And if you're doing triple science, you've already done the stuff for paper 2. So nuclear fusion, is what happens in the centre of all stars. It can also happen in experimental reactors. But the thing is, it's very, very unstable, and you need really high pressures and really high temperatures. And the experimental reactors might only work for a few seconds. So this is very much still an experimental stage. Now, a common thing might be hydrogen, and effectively what you do is you have hydrogen and you join them together, and then this makes helium. And that's the idea, or the ideal thing that we'd have inside a fusion reactor. Because what you could then do is start with hydrogen, which is really plentiful and it's not radioactive. You join it together to make helium, which is not radioactive, and then it might give out some energy. And the whole thing about all of this is that what we're doing as we join these things together is we convert some of the mass into energy. Now, fission is similar, but we break things apart. And the common isotope that we use is uranium-235. And what we do is we have this uranium-235 and we fire a neutron into it. And what that does is it makes the uranium-235, which is slightly unstable, really unstable. And then this uranium-235 basically breaks apart into 2 different things. Now, it changes on depending on what the reaction is, but we've basically got 2 smaller nuclei that it produces, and then it gives out 2 or 3 or 4 neutrons. And this is basically fission, where we break up something really big, and in breaking it apart, we also release energy. Okay, so I'm just seeing what some of the comments are. Yeah. Cool, right, so there's some good stuff there. How did I think the A-level papers went? To be honest, I've not seen them, but I've heard fairly good things about them. So and also some people saying there's other things released. In its simplest format, uranium-235 absorbs a neutron, it breaks apart into 2 daughter nuclei, and then it gives out more neutrons. And these neutrons here could go along, and they could find another uranium-235, and they could then cause that to split apart into other things and give out some more neutrons. And then these neutrons could go off and then go into another uranium. And so this is what we then call a chain reaction, where one reaction causes another reaction that causes another reaction. So this is where nuclear fission can be really useful, because what we can do is we can control that reaction inside a nuclear fission power station. So what's it say you need to know about? It says that you need to know about the unstable nucleus, the uranium-235. It's going to absorb a neutron, and then it's the kinetic energy of these particles that the energy is released in the store of. So basically, the energy stored inside this comes out in the kinetic energy, and what we can then do is we can put this into a nuclear power station. So in a power station, you've basically got a big chamber here where you've got fuel rods which have uranium or plutonium, and this is where we have nuclear fission occurring. We also have things like control rods that absorb the excess neutrons, and that means it means that we can control exactly how quickly or slowly the reaction's happening. And what we do is we pump water into this reactor through a load of pipes, and you pump in cool water, and as it goes through, the water comes out a lot hotter. And then of course the hot water is the thing that turns to steam, and then it turns a turbine, which is very much what you learned about in the very first part of the course. So yeah, I reckon that is basically it. So yeah, draw and interpret diagrams representing nuclear fission and how a chain reaction may occur. Define nuclear fusion as the joining of two light nuclei to form a heavier nucleus. All of that stuff there is basically what I've said there. And that's all there is to it. So I reckon the paper will be fine tomorrow. Normally, from what I've seen and all my experience of being a teacher, is that generally the physics papers from AQA are pretty good. They're always sort of fairly standard. And if you've been doing lots and lots of past papers, which I'm sure you have been, you'll see sort of similar patterns occurring. The main thing is that you just read the question really thoroughly. And then, of course, you just make sure that you do the basics. So this might be drawing a diagram to help explain your answer. It might be selecting the correct equation from the data sheet and writing it down, putting the numbers in, doing the calculation, and then giving your answer with units. So don't forget the units at the end of your answer. Apart from that, if there's any more help that you need, and it's something I maybe didn't address during the live stream today, go and have a look at GCSEphysicsonline.com. I've got videos for every single part of the course. So every required practical, I've got a video about it. Every single kind of bit of theory, I've got worked examples, explainer videos. If you don't understand about transformers or fission or fusion, whatever it might be, I've got videos that explain absolutely everything over at GCSE Physics Online. And if you have seriously just joined at the end, then you can always go back and re-watch the whole thing because it's going to remain live on YouTube for the next few days. Do you want me to do the same thing for paper 2? Let me know in the chat, yes or no. Do you want me to do a similar kind of live stream the day before physics paper 2 for everybody as well? Yes. Soraya, yes. Yes, boss. CR7, yes, please. Natalie, yeah, loads of people saying yes. Right. Also, what do you reckon you're going to get tomorrow? Are you feeling confident? I guess a lot of people having done biology and chemistry. I think biology was a bit more tricky. Chemistry went well, I think. Can you have some questions as part of it as well? Yeah, if I haven't answered any questions here, I do have stuff on my website, A-Level Physics Online, if you want to see some questions there. So yeah, what time? I don't know. Yeah, biology was horrible. Quite a few people said that. I understand that biology wasn't as nice. Somebody's going for the grade 10. Yeah, got to aim high. Why not? What I estimate the grade boundaries, I've got no idea. Basically, ignore the grade boundaries. Just try and get as many marks as possible. Yeah. All right, everybody. Lovely to see you. Don't forget, if you haven't already done so, like the video, subscribe on YouTube, all that good stuff. And if there's anything else you need, head over to GCSE Physics Online.